What's up guys, Mitch back with another video here at 45 Drives. It's been a while since I've been up behind the camera. I've been traveling for about 9 months now, pretty much non-stop. So I'm really excited to get back in and do some cool stuff. So today I'm going to be talking about ZFS, the ARC. Is it still relevant when we're talking about NVMe and super fast storage? And I'm going to use our brand new F-16 model server to show it off. So this thing is really beastly. It uses 15 mil NVMe's rather than the standard 7 mil. It allows us to put 16 up front. It has full 4 PCI Express lanes per NVMe, so we get the full bandwidth of every drive. And it comes with up to a 64-core AMD EPYC CPU. So this thing is a beast. I'm going to be doing lots of content with this over the next while. This is just the first of many. I'm going to be doing Ceph clusters, really showing off what this thing can do. So definitely stay tuned. But for today, we're going to dive in. We're going to do some ARC content. We're going to run some benchmarks, and we're going to get to the bottom of this. Is the ARC still relevant when it comes to using 16 NVMe's in a ZFS array? So come on in. All right, so before I bring up the computer and get the screen cap going, I just wanted to set some context, set some stage for people that may not be super familiar with ZFS. So I said some words in the intro of ARC and ZFS and NVMe, so I just want to make sure that we are all on the same page. So ZFS is really cool because it uses an adaptive replacement cache that's different from other file systems and RAID solutions. If you were to use a standard software-defined RAID with ZFS on Linux, you would be using the page cache of the operating system. ZFS does things differently, where it has its very own segregated, completely standalone cache just for ZFS. And again, that's called the ARC, Adaptive Replacement Cache. So people think mistakenly that ZFS is really RAM hungry and it needs lots of RAM. And that's not really actually the case, but what it it is able to use as much RAM as you can give it. That doesn't mean you have to have a lot of RAM to get a good experience. But the more RAM that you do give ZFS, the better your read performance is going to get. And the more metadata that it's going to be able to cache in memory, making things just feel a lot more snappy. So that's the concept of the ARC. Now, when we think about the ARC and it's running in RAM, we know our RAM is blazing fast and we know the latency is very, very low on RAM. But when we have a lot of NVMe's that can do 3, 4, 5, 6 gigabytes a second each, is the NVMe fast enough that if we disabled that ARC and we were reading directly from NVMe, would we get a performance improvement? Would it be slower? How does that work? So that's what we want to explore today. So I think setting the stage, I think we're ready to go. We're going to jump in and stay tuned for the end because I might show off some potential tunings for ZFS that you can try at your own peril or in testing environments. So let's dive in. All right, guys. So I've now got an environment here set up. I've got an F-16 that I'm SSH'd into. And so what we're going to do is we're going to show off some first preliminary numbers. So what I thought we would do first is I would show off MDADM, so Linux RAID, with a big old RAID 0 and ZFS on top of it. And then we would benchmark that and we would compare that against a ZFS pool with 16 VDEVs with absolutely no redundancy, just to see what the absolute limit of each solution is at this speed with these number of disks. And then we can kind of see what happens when you add redundancy and you start adding layers in. So also one thing I should mention, when I was talking about the ARC earlier, I kind of explained about how cool it is, but one thing I didn't mention is with that standard Linux page cache that other file systems are going to use, it just uses standard first in, last out type of caching. So as new stuff comes into the cache, the older stuff gets kicked out. ZFS has some really cool extras where it not only has that, but it also takes into account how often a piece of data gets accessed. And the more often that data gets accessed, the harder it is to kick it out of the ARC. And so it's going to be cached longer, it's going to remain there. And so anytime you go to read it, you're going to get that performance benefit because it's coming from memory rather than have to read from disk. That's especially beneficial when we're talking hard drives, of course. to start, let's go in and let's create our MDADM RAID 0 array, and then we're going to put our file system on it to get some baseline numbers. So what I'm going to do is, let's just take a look at my history of some of my previous ones so I can copy it. All right, there we go. So actually, let's just do 897. So here we go. We got MDADM, create. We're going to call it devmd0. It's a RAID 0. We're putting 16 RAID devices in it. Our chunk size is 256K, and the reason why we're doing that is the largest that XFS supports. And we're going to be using SDB all the way to SDQ. These don't show up as NVMe devices in this server because this is the UBM backplane, if you recall, which is different from standard NVMe switches. All right, so let's create that MDADM array, and there we go, it is now created. So next, let's create our XFS file system. What's really cool about XFS is that it's actually going to know inherently the chunk size of this array, how many devices are underneath the hood. We can specify that with XFS, make XFS commands, but XFS is smart enough to know, so I don't have to do it. So what you're going to see here is it's going to create that file system, and it's already done, which is great. Now let's mount it. Dev MD0 over at mount RAID 0. And so let's run our first test, and let's just see how much write performance we can get out of this thing. Remember, 16 NVMe's, full 4 PCI Express lanes. So let's grab one of my FIOS here. All right, so what we're doing, and actually I should preface this right now, all the tests we're going to be doing here is all sequential throughput. That's what we're trying to get. Maybe we'll do another test or another video tuning for IOPS performance in NVMe, because IOPS obviously is very important when it comes to this type of server. But we're just trying to get as much data down the pipe as we can get in this video. So let's start with our sequential write performance. So here we go. And we can see here we're using a 1 meg block size to signify large file. We're putting a high I/O depth because it's a very sequential file in nature, which would be able to send a bunch of I/O down the pipe very, very quickly. So a high queue depth makes sense. 100 gig is the size we're going to be using. We're using direct I/O, which means we are bypassing memory as much as possible. It's a time-based run, so we're going to run for 60 seconds. I won't make you sit through all 60 though, I promise. And we're doing 4 jobs. And the reason why we do that is we can do a single job, but we're not going to actually see the full performance of the array if we do that, because we're going to be bottlenecked at that point by a single CPU core, because the number of jobs is exactly how many threads, Linux threads it's going to use. So if we did this with 1, we'd be able to watch top and we'd see that 1 core would be at 100% usage, and the performance wouldn't be as much as we could get out of this thing. So we want to make sure that we are giving it enough CPU to give enough performance to show off what this can do. And then group reporting just takes all of those 4 jobs and coalesces it into a single report for us. So let's run it for us right now. And that looks terrible. Oh, I guess first things first, I should CD into the directory, right? 500 megabytes, that seems a little suspicious. We are on an SSD boot drive, which limits at 500 megs, so that's how I knew right away. All right, let's pop into the directory and let's do this right. There we go. And let's try that again, shall we? That looks a little better, I think. 21, 22 gigabytes. That makes more sense to me. All right, so we're sitting in here at 21.3 gigabytes a second. So the NVMe's are not in this server, and the one that's in the lab are 960 gig, 15 mil, Micron 7450 Pros or 9300 Pros, one of the two. Anyway, I checked the spec sheet. So they actually don't have a fantastic write throughput performance because they're smaller NVMe's, they're only 960. So they can do about 1.3 gigabytes a second throughput each. So if we do that math, 1.3 times 16, 20.8, and that's about what we're getting, a little higher, which makes sense. I mean, it will be a little over spec. So we're about right on. So what we're seeing here is a pretty much lossless performance. This file system is able to give us all of the I/O that is available to us. When we don't have any parity there, it can actually deliver pretty much what that system can do. Now, the reads on those NVMEs are actually quite a bit better, thankfully. So if it's 1.3 gigabytes a second write, it can do upwards of 3.5 gigabytes a second read. So we should see, when we run this test again with read performance, is we should see a much better number if we can get full scaling. So let's try. Okay, so now we're going to use that same file we just laid down, and we are going to run the read performance. And look at that. We are about a little over double of our performance of our write. We're writing at 52.3 gigabytes a second, which is about probably 56 gigabytes a second. So again, pretty much no scaling or full scaling there, which is amazing, right? The only thing that really I want to kind of throw a wrench in the whole works here is, unfortunately, MDADM, once you start throwing some parity in there, really starts to come down in performance. You can still keep the read performance pretty high, but write performance is going to suffer tremendously when we start doing RAID 6, RAID 5, RAID 10s in an MDADM array. So I know it's a little bit of a spoiler alert, but ZFS, even though it has a lot of optimizations to go to really be king for NVMe and really to be able to get the most out of NVMe, kind of is the best software-defined RAID solution we have in Linux for single server. All right, so there we go. So our numbers, 56 gigabytes a second read performance. Darn. Let's try it with ZFS with no redundancy whatsoever. So let's clear that out. Let's get out of that directory. Let's unmount it. Let's, oh, am I still sitting in it somewhere? Oh, I'm sitting in it up here. Mount. There we go. Okay, so let us now stop our array. AMD stop, dev MD0. Am I still sitting in that darn directory? There we go. Mount RAID 0. And let's stop the array, and let's wipe our file system, or wipe our disks rather. Okay, so we're back to baseline. Now let's go ahead and let's do this with a zpool. Zpool create tank dev sd b to q. So no redundancy again, right? And let's see what this pool looks like. So if we do a zpool status, we can see we've got 16 individual VDEVs. Not quite the same as a RAID 0. ZFS works a little differently. I think I've talked about this in a lot of other videos, but it doesn't quite do striping, but what ZFS does do is puts I/O to different VDEVs. So similar to the way striping works, but not quite the same. Okay, so we've got our zpool. Let's try our numbers on this one, and let's see if it can keep up with XFS. Spoiler alert, I don't think it can. Oh, was our... Actually, at the same time, let's throw an I/O stat. Let's see how busy our disks are while we do this. So let's full screen this bad boy, and let's run our write performance test. Did I do it again? You know I did it again. Oh my God. Tank in this case. Okay, we're sitting in tank. I think I'm a little rusty. It's been a while. All right, so let's go again. Here we go. Write performance on our ZFS array. That's nothing to sneeze about. You can see it's going up and down. Why is that? Well, ZFS works very differently. ZFS is doing transaction group flushing. So ZFS is going to load a bunch of writes up into RAM, coalesce those writes, and it's going to flush them in transaction groups around every 5 seconds. Sometimes less, sometimes it can potentially be more, even if it's set to 5, which is the default. Maybe that's one of the parameters you could potentially tune as a lever to, say, improve performance in certain scenarios. Of course, every time you tune something, it's going to be at the mercy of something else. It's a give and take, which in this case, it would be safety of your actual data, because you're letting the data sit in RAM longer before it flushes. So if you have some very fast NVMe, that might improve things. We'll find out. But it means that if power outage happens in that amount of time, and because you're not doing sync writes, you could potentially lose those writes. So there's always going to be trade-offs. All right, so we can see here, we got about 19 gigabytes a second I/O, so very close to the XFS solution. But let's see what we get when we try our reads. Are we able to scale as well in reads? Unfortunately not. But still respectable in my opinion. We're still doing 20 gigabytes a second, 21 gigabytes a second. That's nothing to be upset about, especially because as we're going to see, when we throw some redundancy in there, we still get some pretty good performance with ZFS. Whereas, like I already alluded to, in MDADM, fortunately is not the case. There's things you can do. There's some tuning, of course, but if you have an MDADM array and you have a ZFS array and you have the same type of redundancy profiles, RAID 6 versus RAID Z2, same number of disks, yeah, ZFS is definitely going to outperform it on the writes by quite a big margin. All right, so I think we can stop this. We have a pretty good idea, right? About 22, that's where it's going to be. All right, so pretty cool. So now let's create a ZFS array. And let's put some real redundancy. Let's actually just go straight up mirrors, right? That should be the worst case scenario for writes. For reads, it should be pretty good because there's no parity. It's going to be reading from all the disks. Let's take a look at what we get here. All right, so let's destroy. So that's gone, our ZFS array. And now let's create a new one. Another thing that's cool you're going to see when you have IO stat running and you create a Z pool, you can see the way that the ZFS lays down the partition table of all the disks. It goes one by one by one, so you can kind of see a waterfall of the disks. Let's show it off here. So let me find my mirror. There we go. So let's go Z pool create. We're going to create 8 mirrors of 2 disks each. So 7, 5, 8. And so watch this. So we can see as it's falling down, as it goes, oh, and now it's got all the disks. So that was actually a really quick one. Sometimes it's a little slower and you can see it better, but all right, so that's really cool. So now we can go back to our tank directory and let's run our first write benchmark so we can warm up our ARC cache, and then we can run our read performance and see what happens. And actually, let's see what happens on IO stat when we do our read too, right? Because we're writing right now and we can see very clear IO on the writes, and we can see it happens in transaction groups, right? It flushes. Writes, stops. Writes, stops. Those are those transaction groups running in real time. So we can see that we lost a little bit of performance on our writes, but darn, not a whole lot. It's really efficient at flushing that IO and maintaining performance. So we can see it goes up and down a bit. It's a little, I guess, more wavy, but still very, very good, respectable performance. And we only have half of the NVMe's now for actual writing I/O because we're mirroring. So really, really cool. So we'll let this finish so we can have a fully laid out file here so we can actually get to our real tests. What we want to see today is that ARC and that read performance. Okay, so we'll wait for IO stat. So IO stat is now cleared out. We're all on 0 IO. And now we're going to do it with reads. And this is, again, our mirrored pool. And let's take a look here. Now, what you're going to notice is we are now reading at 18 gigabytes a second. But look at that IO stat. Nothing is coming from our disks. And that right there is what ARC is, the Adaptive Replacement Cache, because we wrote that file to the ARC, and there's no I/O going on otherwise, and it's a very new pool. Every bit of that file got sucked into the ARC, into the RAM, into the Adaptive Replacement Cache, and now every bit of the I/O coming from this pool is coming from RAM, which is pretty interesting. And so we would get some amazing performance benefits from this if we're doing hard drives or SSDs. Now we know that our NVMe's can read at much, much faster than this, but of course, again, there's still a lot of optimizations that need to be done in the ZFS code to really get ready for what's coming and how fast these NVMe's are. ZFS has been around for a long time before Flash was anything even remotely mainstream. And so while there is work being done, it does take time. Okay, so there we go. We've got our read performance done. Now let's go ahead and let's ZFS set primary cache to only metadata. I would never recommend, even if I said that we should turn off the ARC, I would never recommend turning off for metadata because that just doesn't make any sense. Why not pull all of your metadata from super snappy, fast RAM? And then also it causes a lot less I/O from your disks that you're pulling the actual data from. Let's let the RAM handle the small metadata I/O, and let's let our disks do what they can do best and pull that big, large file data out of there. So we are going to set that on our tank, our pool. And so now, unfortunately, we have to rewrite again because even though we disabled the ARC, if we tried to read that file again, it would come from the RAM. So let's go ahead and write a new file. We'll call this test2.file. And I will just skip forward for you guys on this part because this is something you've already seen. Okay, so our writes are finished. So now let's rerun our read test and let's see if we can beat that 23-ish gigabytes a second that we get with the ARC enabled for our writes. Let's just go ahead and we'll switch this over to our read. Oh, and look at that. We can already see that our reads now are coming from disk. And unfortunately, those reads are coming from disk at a much slower speed. Not because the NVMEs are not capable of it, of course, but it's just inherent to the ZFS code not being efficient enough to be able to pull from those NVMEs fast enough. So we can see we're doing 11 gigabytes, about 12-ish something gigabytes a second. So not slow by any means, but still slower than using the ARC. Now, when would I recommend you turn off primary cache all and set it just to metadata? Well, in the case that maybe you know you have a data set that is so large that it definitely could never fit closely into the ARC, and let's say that's a data set that is like a machine learning data set that you're running over and over again, and what you'll end up getting is potentially some cache thrashing back and forth, reading one from prefetching some, not prefetching some others. So what you could get in that case is a benefit by setting the metadata as the ARC only, but definitely do some testing, make sure that is the case, because there are some times where you can still benefit from the ARC. So we can see that definitely ARC is still viable in today's day and age, even with our NVMe. Maybe that won't be the case someday, but right now it certainly is. So before I finish, let's take a look at some possible tunings that we have at our disposal. First one I would say is the scheduler for your disk. You should be using scheduler none for your disk. So if we take a look right now at what the scheduler for a disk is, bet you it's not none. Let's take a look. So if we cat sys block, let's just do SDE. Sysblock SDQ, EQ scheduler. Yeah, we can see it's currently set to Kyber. So ZFS prefers to use its own IO scheduler. So what it recommends is setting the IO scheduler to none for ZFS. So first things first, let's go ahead and let's turn our cache back on. Primary cache, all tank. And so now let's go ahead and let's go through and set the scheduler of all of our disks to none like ZFS recommends. So we could do a nice little loop for this for I in. So I have B, C, D, E, F, G, H, I, J, K, L, M, N, O, P. Never thought you'd be learning your ABCs with me, did you? All right, let's go ahead and echo none sys block SD $I Q scheduler. Done. So that went through and it should have set it to none. So, but let's check SDE to see if it did. And we can see now it has moved over to none. All right. So now we have the scheduler disabled. So that's one thing we can do. Let's take a look at another thing. This one is not going to benefit you most likely for throughput, but it is one I should mention for people that are doing latency sensitive workloads or want very, very high IOP workloads, which we're not really touching today, but this one is really good. So this is the sleep states of your CPU. So if we take a look at, so let's use this guy up here. So if we watch cat proc CPU info grep mhz, we're gonna have to do this with some quotes. So we can see our CPU cores are sitting around 2.3 gigahertz as a 64-core CPU. We have some cores that jump up to 3 gigahertz every now and then because we have sleep states enabled. The cores will essentially park themselves, go to a lower power state, which is great, gives you power savings, but in a lot of cases, if you have very, very fast interrupts, fast CPU calls that are coming in, it requires the CPU to come back up, clock itself back up, and then do the work. So if we have low latency workloads that we want to hit, we may want to disable those. So if we watch this right here, we can see 2.3 gigahertz is what we're sitting at. What we're going to aim to do is see this to go back to full clock speed on all of these CPUs. So we have a little loop here that we can do as well. So we can see we have the CPU state, and these are the states of the sleep states. There's multiple different ones, and we're just going to echo 1 into the disable, saying yes, we want to disable it. So, and for all 128 cores, or 64 cores, 128 threads. So let's do it with the first one. Copy. And let's do it now with state 2 as well. So now what we're going to see is, we can already see it, those cores are now popping up to 3.1 gigahertz, every single one of them there. So that has done its job, and that has set that. Again, this is actually probably going to hinder our performance in this case, so we're going to echo 0 to them. But yeah, that's something you're going to want to do, look at potentially doing, right? Anything I suggest in here, definitely test. That's how you do tuning. It may help certain workloads, it may hinder others. So tuning is always great if you don't have a multi-use case file system, a multi-use case solution, because it allows you to tune specifically for that one use case. When you have lots of different workloads, large blocks, small blocks, sequential, random, it's really hard to hone in on a single thing fits all tuning, but there are some things that can help a little bit. But where you're really trying to tune for one specific workload, that's where you get your biggest benefits. But if you're trying to tune for lots of workloads, don't expect to get a 30 or 40% performance bump, because it's just across the board, because it's just not going to happen. All right, so let's disable state 2 and let's disable state 1, and we'll go back down. We can see we're back down on our clock speed. All right, so 3 ZFS tunes that I wanted to talk about: Zfetch array read size, Zfetch max distance, and transaction timeout. So these are 3 that we can potentially play with. So if we look at the defaults for these, I believe this one is 1 gigabyte, this one is 8, and the default for this is 5 seconds. So let's just set these quickly and let's see if it gives us any performance benefit. Maybe it will, maybe it won't. ZFS has great manual pages where you can go in and you can read all of these tunings and when you may want to change them and what they're actually doing. So I encourage you to go in and take a look at these for sure. The transaction timeout is great. It's how long before it flushes that I/O like I talked about before. All right, so ZFS sys module, ZFS parameters. Okay, echo. So let's go 15. Sys modules, ZFS parameters, and it's called ZFS TXG timeout. Okay, so we just pumped that up to 15 seconds. All right, so next one, let's change this to 4 meg. Boom. Copy that. Okay, so this is Zfetch array read sizing. Oh, permission denied. Maybe we can't change that one with a live pool. Okay, we'll leave that for now. Let's see if this one will let us change it. Let's just see, I'll put the wrong parameter in first. Okay, so it did accept it. All right, so let's go ahead. Let's increase that to the 16 megs. All right, so let's run some tests. First, we'll do our write again, and then we'll warm up that cache, and then we'll try a read, and we'll see if we've improved anything at all. All right, here we go. So we got 18 to 20 gigabytes a second, so a little improvement on the writes. Let's see if we can make any improvements on the reads or if we're kind of just stuck. Typically what I've seen is that scheduler, that changing will give me about a 1 to 1.5 gigabytes a second improvement. Not crazy, especially when you're dealing with performance this high, but and you can see here in this case, it looks like we've actually reduced performance a little bit. So there's that trade-off that we talked about. And that's where tuning is going to be really something you're going to trial and error for different workloads and different use cases. The two that I definitely know will improve things, like I said, is the scheduler and setting those CPU states for your IOP workloads. Also, playing with tuned profiles can always help as well, especially if you're doing stuff over the network. Doing network tuned profiles, that can help as well. So we'll let this play out and then we will call it and we will wrap. I would love to show you guys some MDADM RAID benchmarks on these disks. Unfortunately, because like I said, you have to resync the array, we would be here for 2 days before it happened. But I encourage anyone with disks out there to go try your own. See if you can reproduce what I've reproduced here and see if you can get MDADM to perform faster than ZFS. That would be really cool. And let us know. So we can see about 20.7 gigabytes, 22 gigabytes a second, a little reduction there. All right, so that, I guess, sums it up. So we know that the ARC is still viable in today's day with NVMe in the solution, which kind of knew all along, but it's a cool thing to explore and take a look at. Maybe we'll explore again if we get any more optimizations in the ZFS code. So if you have any questions, if there's any videos that you'd like to see in the future from us, definitely let us know. But I'm going to be putting together some very, very fast Ceph clusters in the near future, so look out for that. But yeah, that's about it. Thanks for coming along for the ride. See you guys.